In 1981, at a conference at MIT's Endicott House, Richard Feynman walks to the microphone and tells a room full of computer scientists that they are about to hit a wall. The universe is quantum. Their machines are not. Simulating reality, he says, would require something we have not yet built. This is not a video about that wall. This is a video about what we have built since. We are going to walk it top to bottom from 1 qubit to 1,000,000. What it is, how it works, what runs in 2026, where it cracks, and what it will and will not do. No metaphors, no spinning coins, the math itself. Start at the bottom. A bit is one number, 0 or 1, nothing else. Every computer you have ever touched runs on these. Billions of switches, each flipping 1 billion times a second. The phone in your hand has roughly 100 billion bits in motion right now. They are deterministic, they are precise, they have built the entire digital age. They are also fundamentally limited. The qubit, the thing we replace them with, is none of these things. It is something stranger. A qubit is not a number. A qubit is 2 numbers, 2 complex numbers. We write its state like this: psi equals alpha times 0 plus beta times 1. Don't worry about the brackets and vertical bars. Physicists call that notation bracket. It just means this is a quantum state. The real action is in alpha and beta. They are called amplitudes. Each one can be any number on the complex plane. And there is exactly one rule that must hold. The magnitude of alpha squared plus the magnitude of beta squared must equal 1. Think of it like a recipe with 2 ingredients whose squared portions have to add up to a single whole pie. That is the entire qubit, mathematically. 2 numbers, 1 constraint. The strangeness is not the notation. The strangeness is what those 2 numbers actually represent. Until you look, the qubit really is both 0 and 1 at the same time, in proportions alpha and beta. You can draw the entire space of a single qubit as a sphere. The north pole of the sphere is the state 0. The south pole is the state 1. Every other point on the surface in between is also a valid qubit. Some lean toward 0, some lean toward 1. Some live on the equator, perfectly balanced, exactly 50-50. Physicists call this the block sphere. It is the actual geometric shape of the smallest unit of quantum information. Then you measure it. The moment you do, the strangeness collapses. The qubit chooses. If you measure in the 0-1 basis, you get one of 2 answers, either 0 or 1. Never both. Never a blend. The probability of getting 0 is the magnitude of alpha squared. The probability of getting 1 is the magnitude of beta squared. That is why the alphas and betas had to add up to 1, so the probabilities make sense. So far, so good. Here is the part that is genuinely strange. Once you have the answer, the qubit really is in that 1 state. The blend you had a microsecond earlier is gone, forever. You cannot ask the universe which answer it was going to give. You cannot peek without breaking it. This is not philosophy. It is not a metaphor about consciousness or perception. It is the most carefully verified result in 20th century physics. The qubit really is in a blend until measured. The blend really collapses on measurement. The act of looking is itself part of the computation. Every quantum algorithm has to be designed around this fact. Now scale up. 2 qubits together do not give you 2 amplitudes. They give you 4. 1 amplitude for the state 0-0, 1 for 0-1, 1 for 1-0, 1 for 1-1. The qubits combine multiplicatively, not additively. 3 qubits give you 8 amplitudes. 4 qubits give you 16. N qubits give you 2 to the n. This is exponential growth, and it bites quickly. 10 qubits, 1,000 amplitudes to keep track of. 50 qubits, a quadrillion. 300 qubits, and the number of amplitudes you would need to track is greater than the number of atoms in the entire observable universe. There is no classical computer that can simulate that. Not the laptop on your desk. Not the world's largest supercomputer. Not a hypothetical computer the size of a planet. The information simply does not fit. This is the wall Feynman saw in 1981. The universe is quantum, and the universe stores its own state for free. We do not. To simulate it, we need machines built on the same physical principle. Now wire 2 qubits together. With exactly 1 operation we will get to in a moment, you can produce a state like this. 1 over the square root of 2 times the sum of 0, 0 and 1, 1. This is called a Bell state. And it is the simplest example of something that exists in quantum mechanics but does not exist in classical physics: entanglement. The two qubits no longer have separate identities. Their fates are mathematically locked together. If you measure 1 and get 0, the other will also be 0. If you measure 1 and get 1, the other will also be 1. Always, instantly, even if the two qubits are on opposite sides of the galaxy. Einstein hated this. He called it spooky action at a distance, and he spent decades arguing that it had to be wrong, that there must be some hidden mechanism the math was missing. In 1964, an Irish physicist named John Stuart Bell wrote down a mathematical inequality. If quantum mechanics was right, the inequality would be violated. If Einstein was right and there were hidden variables, it could not be. 3 decades of laboratory experiments, John Clauser, Alain Aspect, Anton Zeilinger, measured the violation again and again and again. The 2022 Nobel Prize in Physics was awarded to those 3 for it. Einstein lost. The universe really is entangled, and we now use that very fact to compute with. Operations on qubits are called gates, the same word classical computing uses for and, or, and not. The first gate to know is the Hadamard gate, written as a capital H. It is the single most important gate in quantum computing. Here is what it does. You give it a definite 0 and it gives you back a perfect blend, a 50-50 mix of 0 and 1. The amplitudes work out to 1 over the square root of 2 for both. If you give it a definite 1 instead, you get the same kind of blend with a minus sign on the 1 component. The Hadamard gate creates superposition. Without it, you have a classical computer that happens to be made of qubits. With it, the door to quantum computing opens. 2 more single qubit gates you will see everywhere. The X gate is the quantum version of NOT. It flips 0 to 1 and 1 to 0. Simple. The Z gate is more subtle. It does nothing to a 0, but it multiplies the 1 component by -1. This is called a phase flip. The minus sign does not change the probability of measuring 0 or 1, but it does change how that qubit will interact with other qubits later in the circuit. Phase is the thing classical bits do not have, and it is what makes quantum computing possible. Hadamard X and Z together can build almost any single qubit operation, and one 2-qubit gate that ties it all together. CNOT, controlled NOT. It takes 2 qubits as input. One is called the control qubit. The other is called the target qubit. The rule is simple. If the control qubit is 0, nothing happens. The target is left alone. If the control qubit is 1, the target gets flipped. That is the whole gate. Watch the truth table. 0, 0 goes to 0, 0. 0, 1 goes to 0, 1, both unchanged because the control is 0. 1, 0 goes to 1, 1, the target flips. 1, 1 goes to 1, 0, the target flips again. CNOT is the gate that creates entanglement between 2 qubits. With just Hadamard and CNOT, you can build any quantum circuit that exists. Let's put everything together and run a complete circuit. The simplest one, the one that creates a bell pair. Start with 2 qubits, both initialized to 0. The combined 2-qubit state is 0, 0. That is our starting point. Now apply a Hadamard gate to the first qubit only. The first qubit becomes a 50-50 blend of 0 and 1. The combined 2-qubit state becomes an equal blend of 0, 0 and 1, 0. The second qubit is still definitely 0, but the first one is now a blend. Now apply a CNOT, with the first qubit as the control and the second qubit as the target. Remember the rule. If the control is 0, do nothing. If the control is 1, flip the target. But the first qubit is itself a blend of 0 and 1, so the result is a blend of 2 outcomes. In the part of the state where the control was 0, the target stays 0. That gives 0, 0. In the part where the control was 1, the target flips to 1. That gives 1, 1. The final state is an equal blend of 0, 0 and 1, 1. That is the Bell state. We just created entanglement out of nothing. 2 gates, 3 lines of code on any quantum computer in the world today. That is the math of quantum computing, end to end. State vectors, measurement, entanglement, gates, and a complete circuit. The rest of this video is about the actual machines that run those gates, what they look like in 2026, what they have already proven, and what still stands between us and the version that breaks the internet. Hardware track 1. Superconducting. Tiny aluminum circuits etched on silicon, cooled to 15 millikelvin, colder than deep space. The qubit is a microwave oscillation in the circuit. Google's flagship is Willow, 105 qubits, and in October 2025, Willow ran an algorithm called quantum echoes 13,000 times faster than the world's fastest supercomputer. Not on random sampling, on a real physics problem. Measuring the structure of 15 and 28 atom molecules, matching nuclear magnetic resonance results, and revealing detail that NMR could not see. IBM, on November 12, 2025, shipped Nighthawk, 120 qubits with 218 tunable couplers. IBM has now publicly committed to demonstrating quantum advantage by the end of 2026. Slide. Superconducting headlines as of May 2026. Google Willow, 105 qubits, single qubit fidelity 99.97%, Quantum Echoes paper, Nature, October 2025. IBM Nighthawk, 120 qubits, 218 couplers, advantage target end of 2026. China's Zhukongji 3.0, 105 qubits, published 2025. 6 billion years on the world's fastest classical supercomputer for the same task. The chip on the left and the chip on the right look almost identical. The Cold War they represent does not. Track 2. Trapped ions. The qubits are individual atoms, usually barium, ytterbium, or beryllium, held suspended in a vacuum chamber by precisely tuned oscillating electric fields. The atoms are manipulated with lasers. This approach is slower than superconducting, but the gates are far more accurate. Quantinuum's Helios system, launched in November 2025, runs 98 fully connected barium ions on a single chip. Its single qubit gate fidelity is 99.9975%. Its 2-qubit gate fidelity is 99.921% across every possible pair on the chip. These are the most accurate quantum gates ever recorded by any platform. IonQ ships its Tempo system in 2026, 256 trapped ions. Slide. Trapped ion landmarks. Quantinuum Helios, 98 ions, gate fidelity above 99.99%. 48 error-corrected logical qubits demonstrated in March 2026 from just 98 physical. IonQ acquired Oxford Ionics for $1.08 billion in September 2025. The pattern is clear. Trapped ion gives you fewer qubits, but each one is closer to flawless. The race is now whether you reach 1,000,000 perfect qubits or 1,000,000 perfect enough qubits first. Track 3. Neutral atoms. Cold neutral atoms, usually ytterbium or strontium, held in a grid of laser tweezer traps, like tiny marbles caught in invisible cups of light. Tens of thousands of atoms can sit in a single machine. Atom Computing, in partnership with Microsoft, demonstrated 24 entangled logical qubits in November 2024, still the standing record. Quera, in early 2026, pushed it to 96 logical qubits on a 448 physical atom array. Atom Computing's next system, called Magni, 50 logical qubits from 1,200 neutral atoms, operational early 2027. Slide. Neutral atoms in 2026. Atom Computing plus Microsoft, 24 entangled logical qubits, the standing record. Quera, 96 logical qubits, 448 physical atoms. Atoms Magna, 1,200 physical, 50 logical, shipping 2027. DARPA selected Atom for its utility-scale quantum program. This is the track that scales fastest. Track 4. Photonic. PsiQuantum's Omega chipset, announced February 2025, runs entirely on single photons traveling through silicon waveguides, manufactured at Global Foundries in upstate New York. PsiQuantum raised $1 billion in September 2025 specifically to build million-qubit machines. Data centers in Brisbane and Chicago, operational target 2027. And Track 5, controversial. Microsoft, February 2025, unveiled Majorana 1, 8 topological qubits on a chip designed to scale to 1,000,000, built on a new material called a topoconductor. If it works, it sidesteps error correction almost entirely. Whether it works, independent physicists are not yet convinced. The path is exotic. The prize, if it pays out, is enormous. Now, the wall. Every quantum computer in the world is fighting the same enemy: decoherence. The technical name for one of the most fragile situations in all of physics. A qubit is a delicate object, a stray photon from a nearby wire, a tiny temperature fluctuation, a faint vibration from the building's foundation. Any of these can knock the qubit out of its quantum state. Information leaks out in microseconds, sometimes faster. If you try to do 1,000 operations on a single qubit, errors accumulate, and your computation drowns in noise long before you reach the answer. The naive solution, just add more qubits, actually makes the problem worse. More qubits means more places for errors to enter, more catastrophe. This is the central reason quantum computing has been 10 years away for 40 years. Without solving the decoherence problem, none of what we just walked through matters. With it, everything does. The fix is called quantum error correction. The idea is borrowed from classical computing. You encode one logical, perfect qubit using many noisy, imperfect physical ones. Voting, redundancy. The same basic principle as a RAID array in your file storage, but applied to quantum information. The dominant scheme is called the surface code. In December 2024, Google's Willow chip published the most important result of the decade. They built logical qubits at 3 different sizes, what physicists call distances 3, 5, and 7. As they made the codes larger, the logical error rate dropped by half at each step. For the first time in history, adding more qubits to a quantum computer made the errors go down, not up. The field had a name for this moment: below threshold. It was the green light the entire community had been waiting for nearly 30 years. The catch with surface codes: they are expensive. To get one truly reliable logical qubit, you need roughly 1,000 noisy physical ones. To break RSA encryption, you would need millions. Then in 2024, a team at IBM led by Sergey Bravi published a different kind of code, a quantum low-density parity check code, QLDPC. Their code encodes 12 logical qubits using just 288 physical ones, roughly 10 times fewer than the surface code, for the same level of protection. In March 2026, Quantinuum used a similar approach to demonstrate 48 error-corrected logical qubits from only 98 physical ones. IBM's roadmap for 2026 includes a chip called Kookaburra, the first processor designed from the ground up around QLDPC memory. The qubit wall is moving. Fast. What is all of this actually for? 3 things mainly. Chemistry, simulating molecules too complex for any classical computer. Drug discovery, new catalysts, maybe even fertilizer that doesn't require half the world's natural gas. Optimization, logistics, finance, materials design, real-world combinatorial problems classical computers struggle with. And cryptography, Peter Shor's 1994 algorithm, which efficiently factors large numbers and breaks every public key encryption system in commercial use on the internet today. The first one, chemistry, is already happening today. The second is happening soon. The third is the reason every intelligence agency on Earth is paying very close attention to this field. Slide: useful quantum advantage demonstrations as of May 2026. Google Quantum Echoes, 13,000 times speed-up real molecular characterization, October 2025. QCTRL, 3,000 times speed-up in materials discovery, May 2026. First claimed practical advantage in industry. Quantinuum H2, error-corrected molecular hydrogen ground state energy to within 0.018 Hartree. The benchmarks are no longer toys. And what it will not do. Quantum computers will not browse the web. They will not play games. They will not replace the chip in your phone. They will not on their own be general artificial intelligence. They are extremely fast at one very narrow class of problem. For everything else, they are slower than the laptop you're watching this on. Then there is Q-Day. The moment a quantum computer factors RSA 2048 and breaks every public key signature in commercial use. Until 2025, the canonical estimate was 20 million qubits running for 8 hours. In May 2025, Craig Gidney at Google published a new paper, under 1 million qubits, less than a week. The line is moving toward us. Encrypted data being intercepted today can be stored on tape, waiting for the day a real Shor's machine boots up. The strategy has a name: harvest now, decrypt later. Slide: the 2026 timeline. Gidney 2025, RSA 2048 in under 1 million qubits, less than a week. IBM target: quantum advantage by end 2026, fault tolerance by 2029. Google publicly estimates Q-Day possible as early as 2029. NIST FIPS standards 203, 204, and 205. Post-quantum cryptography, finalized 2024. U.S. National Security Memorandum 10. Federal agencies must migrate by 2035. The decade is real. 800 years ago, Leonardo of Pisa wrote down a sequence about rabbits. Today, that sequence is inside Chrome. 45 years ago, Richard Feynman walked to a microphone and said reality could not be simulated. Today, in 2026, dozens of machines on 3 continents are slowly, painstakingly becoming the things that can. Math is patient. The wall is moving. You are watching it come down. This is NITH signal. No hype, no noise, just the signal.